CCI, Crash Course Instrumentation, presents Saturday Special Episode 13, History of Threaded Fasteners. Standing credits. Thank you to Tony R. Kuphaldt and the open source community for the Model project. Hook this tiny spiral built the modern world. Today, we'll speed tour the history of threaded fasteners, how we went from wooden screws to precision machine threads, why the United States embraced Phillips, even though Canada had a brilliant Robertson design, and what every technician should know about torque, locking, and safety. Roadmap. Origins. Standardization. Drive designs, slotted to Torx. Phillips versus Robertson. Thread systems. Unified, metric, pipe. Torque and locking. What matters for electricians. Origins. The first threads. The idea is simple. An inclined plane wrapped around a cylinder. Ancient engineers used wooden screws for presses. The Archimedes screw moved water using a helical surface. By the late Middle Ages, metal screws appeared in instruments and armor, but hand-cut threads varied wildly. No two makers had the same pitch or angle. Industrial Revolution, make it interchangeable. Standard parts needed standard threads. In the 1800s, Sir Joseph Whitworth proposed a 65-degree thread with specific pitches in Britain, an early national standard. In the United States, William Sellers introduced a 60-degree thread form with a flat crest and root. This became the U.S. standard, the ancestor of today's unified threads. Standardization meant you could build a mill in one city and repair it with bolts from another. Head and drive types. Why slots gave way to sockets. Slotted. Screws were first because they're easy to make, but the driver slips off center and damages the work. Square socket, Robertson. Cross-shaped, Phillips. Frearson, also called Reed and Prince. Hex socket, Allen, and later Torx, all attempt to center the tool, reduce slip and speed assembly. Each drive balances three things: self-centering, torque capacity, and cam out. The tendency to kick the tool out before the fastener breaks. Why the U.S. adopted Phillips over Canada's Robertson, Canadian inventor. P.L. Robertson patented the square socket screw in the early 1900s. It centers well, resists cam out, and drives fast. Objectively excellent for assembly work. Early Ford Motor Company. Trials reportedly loved Robertson screws for speed, but long-term supply concerns and strict licensing limited U.S. adoption. Enter Henry F. Phillips, who championed a cross-shaped design that intentionally cam-outs at high torque. On early power drivers, cam-out protected parts and tools, acting like a crude torque limiter. Just as important, Phillips's business model made it easy to license and manufacture across many suppliers. The result? Rapid U.S. adoption in mass production, even though many technicians still prefer the Robertson drive for control and torque. Thread systems you'll meet in the field. Unified Thread Standard, UTS, in North America. UNC, Unified National Course, and UNF, Unified National Fine. Major diameter and threads per inch define the size, for example, 1/4 inch, 20 threads per inch. Metric ISO threads, size by nominal diameter, and pitch. For example, M6x1 means 6 millimeters major diameter, 1 millimeter pitch. The thread angle is 60 degrees, like unified, but dimensions and tolerance systems differ. Pipe threads. NPT, National Pipe Taper. Seals by wedge action and thread interference. Good for pipes, not for instrument panels. NPS, National Pipe Straight, needs a gasket. International work may use BSP, British Standard Pipe, which looks similar but is not interchangeable. Check before threading. Left-hand threads. Show up where rotation would loosen a right-hand fastener. Bicycle pedals, propane fittings, some fan blades. Look for the LH mark. Strength, grades, and materials, plain language. In unified, say grades, use marks on the head. For example, 3 marks versus 6 marks. In metric, property classes like 8.8, 10.9, and 12.9 indicate tensile strength levels. Stainless resists corrosion but can gall, cold weld, under load. Use proper lubricant or anti-seize where required. Platings and coatings combat rust but change friction, which changes the torque needed to achieve clamp force. Torque, preload, and Y Gorilla Tight is not a spec. Torque is the twisting force you apply. Preload is the clamp force created as the screw stretches slightly like a spring. The goal is consistent preload so parts don't slip. Too little torque and vibration loosens the joint. Too much and you yield or break the fastener or crush the parts. Because friction eats most of your torque, lubrication and surface finish matter. Follow the spec. Dry versus oiled torque values are different. Keeping fasteners from loosening. Lock washers. Split rings. Add spring but are not magic. Under vibration they can flatten. Nylon insert lock nuts. All metal lock nuts. Prevailing torque nuts. And chemical thread lockers, medium or high strength, are stronger options. Mechanical retention. Safety wire, cotter pins, tab washers, prevents rotation entirely and is used in high-consequence applications. Vibration testing, like the Junker test, shows why proper preload and locking beat Tighten and Hope. Electrician and Instrumentation takeaways. Terminal lugs. Use the specified torque, so copper strands are clamped, not cut. Overtorque can cold work copper and lead to hot spots. Choose the right thread system and drive for the environment. Stainless in corrosive areas, anti-seize for stainless to stainless, and avoid mixing metric and unified. For enclosures and panels, prefer machine screws with straight threads and proper washers or thread-forming screws designed for sheet metal. Avoid tapered pipe threads except where specified for fluids. Fun historical footnotes. The Whitworth thread helped the first global maintenance economy. Spare parts by mail. Early assembly lines loved Phillips because cam-out reduced broken bits and stripped heads before torque tools were precise. Robertson became a Canadian staple, so common that many North American wood screws still ship with square drive options today. Wrap threads turn Torca into a reliable clamp force. Know your drive types, match the thread system, use the right torque, and lock it when lives or uptime are on the line. Thanks as always to Tony Kuphaldt and the open source community. If this helped, like and subscribe to Crash Course Instrumentation.